Okay, so this is the next part. So we've done the mesh. The next part will be setting up the solution so that we can run it. So I've updated the mesh module. So I just right click and press update. We've got the green tick. So now let's head into setup. So right click and edit. And it will open up the Fluent launcher here. So we're in 2D, double precision, just quicker. And then over to processing options where we're going to select parallel. Now the laptop I'm using is 6 cores, so I'm going to go for 5 processors. So it's going to be using 5 of the available 6 cores. You could use all 6 or however many you have if you want, but it's just good practice to just leave one core free. So yeah, 5 processors, 2D, double precision, parallel, 5. Hit OK. So now Fluent's going to open up. Okay, so we've got our domain here. So the first thing that we're going to do is head over to models here on the left. So in general, you kind of want to head in order here. So this list, this ribbon here is arranged in the order you want to kind of move through it. So we're starting at the top. The first thing we want to do is define the physical model. So the minute it's set up to be viscous laminar. If we go to edit, what we want is we want to choose K omega. That's the turbulence model we'll be using, specifically the SST. So the SST K omega model is good for external aerodynamic flows like this, where you've got aerofoils at high angles of attack. There's likely to be separation. This turbulence model is good at predicting the separation, and so it should be accurate. Hit OK. Close the model section. The material just contains info1 air, so you can have a look at that if you want. This is where the viscosity is obtained from, the one I mentioned in previous parts. So we can, that's all fine. Boundary conditions. So inlet, as you can see, it's already recognized what we named the inlet as the velocity inlet. So just double click that. So as you guys know, we will be moving at 12 meters per second. Magnitude normal to boundary absolute. So now the turbulence specification method, I'm going to change this to intensity and length scale. So the turbulent intensity just refers to the amount of turbulence in the free stream air in the domain. So for real life still air, it's going to be very, very low. So a number that I've used in the past is 0.3. And the length scale refers to the size of the turbulent eddies, the smaller scale turbulent eddy sizes that you'll see. That is an empirical formula that I used for my dissertation, which I've got here. So based on the characteristic length, the turbulent length scale will be 0.0525. So I'm just going to copy that and put it in here, 0.0525. That's okay. I'm going to do the same for the pressure outlet. So this is all fine, this is all default. Now again, change the turbulence specification method to intensity and length scale, the same 0.3 and 0.0525. Okay, so those are matching. That's done internal, we don't need to touch, that's just the internal surface body, the fluid area. Wall, just double check that these are all correct, they should be by default. So flap 1 should be a stationary no-slip wall, so stationary no-slip wall, that's all good. Check the same for flap 2. Again, stationary no-slip wall, that's all good. Main plane should be the same again. Main plane, stationary no-slip wall. And finally, walls referring to the top and bottom boundary. We said earlier that we wanted stationary slip walls. So head over to specified specified shear here underneath shear condition. Make sure these are on 0. So there we go, we've defined our slip walls for the top and bottom, or our infinite boundaries. Reference values, so these will be used to compute the lift and drag values that will produce. So just change this to compute from inlets. So the area is going to be the chord times the length, or the span, sorry. So it's going to be 0.75 times by 1. So the 1 is the span, is the approximate length we have between the inner surface of the rear wheels of our car. And then 0.75 is the projected chord length. So density is fine, depth is fine. Leave that. Length changes to 0.75. This is all fine. Velocity is fine. Reference zone is surface body. Okay, that's that all done. Reference values. Next we move on to methods. Not to go into too much detail, but leave this all on defaults. Okay, just for now. Momentum, first order, specific dissipation rate, first order, turbulent kinetic energy, first order, momentum, change this to first order, pressure, second order, and then that's that for now. Controls, leave these as they are. Report definitions. So now we're going to add our lift and drag monitors so that we can monitor the convergence of lift and drag as the program simulates or iterates. So new, force report. Let's start with drag first. Drag, name that drag. Drag coefficient is what we want, and we want it on the flaps and the main planes. We want a report file and also a report plot. So the plot will it will plot as the program iterates, and we'll see that on the screen. So drag, blah blah blah. That's all done. Coefficient. Double check that. That's done. Do the same again, but this time for lift. So force report lift. Coefficient again for the airfoil. Change this to lift. We want a report file and a report plot. That's all fine. Close that. So we've got our report definitions here. So after we've iterated and the simulation is finished running, we can head over to compute here, and it will print out the lift and drag values into the console here. So we hit to monitors, residual. We're just going to change the criteria for continuity. Just add a 0 there. And deselect check convergence on all of these. Okay, just for continuity. This is the one we want to keep an eye on. This is the most important residual. Hit OK. Report files. Drag and lift there, report files. Report plot, sorry, drag and lift there as we want. Ignore convergence conditions, head over to initialization. We want hybrid initialization. You don't need to touch anything here, just hit initialize and it will do a quick 10 initializations just to, as I said before, initialize the flow field. So calculations, activities, double click here, run calculation. Change this to 1,000, which should be more than enough. And before we calculate, let's include all the data file quantities just for post-processing, just in case. So just click here to select all 76 additional quantities. We may find it useful to have ones like pressure coefficient here, things like that. So now we're all good to go, and we hit calculate. You'll see it will start. It will bring up the residuals, the scaled residuals, the lift and the drag plots. And we'll be able to see how they behave as the program iterates. So you can see it moving along quite nicely. It's 2D, so it shouldn't take too long. Okay, so we finished after 104 iterations. The solution is converged. So we can see the lift and the drag values that we're getting. So what I did first of all is I started calculating using first order discretization schemes. So if I go back to methods here, you can see momentum, TKE, and specific dissipation rate is all first order. Just to give some stability to the calculation, by using first orders, it reduces the chance of you getting wildly oscillating residuals. So I've done that with first order. I'm now going to switch to second order as they are more accurate. And then I'm going to rerun the calculation for another 1,000 iterations. Again, that should be more than enough. Hit calculate. Okay, and we should see it begin again and start iterating. Okay, so we're back. Our solution is converged using the higher order discretization schemes. So this is good news. It took 414 iterations. Let's have a look at our drag plots. Again, nice and stable, no fluctuations. You can see the result we got using the first order schemes and the second order schemes. So there is quite a bit of error between the two. Let's look at lift. Lift is pretty much the same. Yeah. So we're done. Let's compute our lift and drag. Let's get some numbers. So if I compute drag, compute lift. So you can see our lift coefficient is minus 2.4, so we're producing downforce, which is good, and a reasonable amount. Our CD is 0.09, so we're not producing bucket loads of drag, which is good. So we're all done for the processing stage. The next stage would be to post-process these results, which will be in the next part of the tutorial.